All right, so we're in chapter 13. We're going to be learning about ANOVA, which is the analysis of variance. So we're on page 1. This chapter introduces one of the most widely used tools in psychological research and psychological statistics, known as the analysis of variance. It's usually referred to as ANOVA. The technique was developed by Sir Ronald Fisher in the early 20th century, and it is to him that we owe the rather unfortunate terminology. The term ANOVA is a little bit misleading in two regards. First, although the name of the technique refers to variances, ANOVA is concerned with investigating differences in means. Secondly, there are several different things out there that are all referred to as ANOVAs, and some of which have only a very tenuous connection to one another. So at the end of this chapter, we're going to introduce a range of different advanced ANOVA methods that apply in quite different situations. But to start out, we're just going to consider the most simple form of the ANOVA, the analysis of variance, in which we have several different groups of observations, and we're interested in finding out whether those groups differ in terms of some outcome variable of interest. So this is the question that is addressed by a one-way between groups ANOVA. The structure of this chapter is going to go this way. So first we're going to introduce a fictitious data set that we're going to use as a running example throughout the chapter. Then we're going to describe the mechanics of how a one-way ANOVA actually works. Then we're going to focus on how you can run one in the statistical software JASP. These two sections are the core of the chapter, and then the remainder of the chapter is going to discuss a range of important topics that will inevitably arise when you actually run the ANOVA, namely how to calculate effect sizes, post hoc tests, and corrections for multiple comparisons, and the assumptions that the ANOVA relies upon. We're going to talk about how to check those assumptions and some of the things that you can do if the assumptions are violated. We will talk a little bit about relationship between ANOVA and the other statistical tools. And then at the end of the chapter, we're going to cover a few more advanced ANOVAs, including repeated measures ANOVA, factorial ANOVA, and analysis of covariance and COVA. In this chapter, we're going to see a lot of formulas, okay, a lot of equations. Remember that our statistical software that we're going to be playing around with, the JASP software, it's going to do all of the mathematical calculations. The purpose of showing these formulas is going to explain what is essentially happening behind the scenes in the software. So we're going to move on. We're in section 13.1, and so we have our analysis of variance, and then we're going to talk about our hypothetical clinical trial data set. All right, so suppose that you've become involved in a clinical trial in which you are testing a new antidepressant drug that's called joyzepam. So in order to construct a fair test of the drug's efficacy, the study involves 3 separate drugs that will be administered. One is a placebo, and the other is an existing antidepressant, which is called anxiety-free. actually, the anxiety-free is an existing hybrid medication, so it's anti-anxiety and antidepressant. So let's see, we have 18 participants with moderate to severe depression. They have been recruited for the initial testing. Because the drugs are sometimes administered in conjunction with psychological therapy, this study is also including 9 participants that will be undergoing cognitive behavioral therapy, CBT, and then 9 participants who are not undergoing CBT. Participants are randomly assigned, double-blinded, to a treatment. All right, so we have our randomized design, double-blind design to eliminate bias, and so they're assigned to a treatment such as we had 3 participants that were assigned to cognitive behavioral therapy, and then 3 other ones that had no CBT, and then they were randomly assigned to one of the 3 drugs. So it could be placebo, it could be joyazepam, or anxiety-free. A psychologist assesses the mood of each person after a 3-month run with each drug. The overall improvement in each person's mood is assessed on a scale ranging from -5 to +5. So with that, as our study design, we're now going to load up our data file, clinicaltrial.csv. So that's the data set that we're going to be essentially, using as our example in this ANOVA chapter. So clinicaltrial.csv has already been downloaded. We can see that this data set, it does contain the 3 variables. All right, so let's go look. So here we are. Here's our clinical trial data, and yep, we have our ID, we have the drug, right, placebo, anxiety-free, or joyazepam, and then we have the third column where the participant would be assigned to maybe no CBT or to CBT, all right? And then we have our mood gain listed here for each of the 18 participants. All right, so let's look here. So again, we can see that this data set contains 3 variables. So we have drug, therapy, and mood gain. So for the purposes of this chapter, what we're really interested in is the effect of drug on mood gain. Okay, so the first thing that we'll do is we're going to calculate some descriptive statistics and draw some graphs. So we're going to do this in our software. To compute descriptive statistics for the mood gain variable, we're going to split by the drug variable. And to obtain a side-by-side box plot, right, we're going to then obtain that box plot for the same variables. So here we go. So we're going to open up descriptives. Okay. We're going to move mood gain to the variables box. We're going to move drug to the split. Okay, go. We're going to get some descriptive statistics. Looks good. I'm going to expand that chart. And all right, so then we're going to go under customizable plots here. and we're going to check box plot. Here we go. All right, and then our results should match figure 13.1. So let's take a look. We're on page 2. So we have our 6, 6, and 6, right? 6 times 3 is 18. We don't have any missing data, and so we see mood gain on the top and the 3 different arms of the study. We have our mean, okay, 0.717, 1.483, and 0.450. We have our standard deviation, so 0.392, 0.214, 0.281. We have our min and our max, so we have 0.2 to 1.2, we have 1.3 to 1.8, and then we have 0.1 to 0.9. So let's make this smaller so we can see our box plots and compare. So we have our anxiety-free, and we see, right, we see our minimum of 0.2, our maximum of 1.2, and we see our median, our mean of 0.717. Then we go to joyzepam here, okay, and we see our mood gain is much higher. It's 1.3 on the min, 1.8 on the max, and the mean is 1.483. And then with placebo, the placebo is min of 0.1, max of 0.9, and the mean is 0.450. So that looks good. Everything matches. So that is what matches figure 13.1. So we used descriptive statistics and box plots of mood gain split by drug. Yep, mood gain split by drug. So as the box plot makes clear, there is a large improvement in mood for participants in the middle group, the joyzepam group, which is the new drug, than there were for either the anxiety-free old drug or placebo group. The anxiety-free group shows a larger mood gain than the control placebo group, but the difference is not as large. So the question we want to answer, the research question is, are these differences real, okay, or are they just due to chance? So we're moving to the bottom of page 2. We're in section 13.2. So how ANOVA works. All right, so let's go here. Go. Right, so we're in our analysis of variance, and now we're looking at the third bullet here, right? So how does it work? How does ANOVA work? So in order to answer the question that is posed by our clinical trial data, we're going to run a one-way ANOVA. So the author is going to start by showing how you do it the long way, right? So by hand calculations. So we're just going to run through that first, and we're going to build the statistical tool from the ground up. So now we're moving to page 3, and then the author is going to take us through showing how you could do it if you didn't have access to any of the cool built-in ANOVA functions that we're using in our JASP software. The author said that they hope that we will read everything carefully and try to do it the long way by hand at least once or twice, just to make sure that we really understand how it works, all right, how the ANOVA works, analysis of variance analysis. And then once we grasp the concept we don't really have to do it by hand anymore, unless we really enjoy math. So the experimental design that the author described in the previous section, it does strongly suggest that we're interested in comparing the average mood change for the 3 different drugs, okay? So in that sense, we're talking about an analysis similar to a t-test, but it involves more than 2 groups. Okay, we have 3 groups. If we let the mean with the subscript P denote the population mean for the mood change that is induced by placebo, and then we let mu A and mu J denote the corresponding means for our 2 drugs, so the A for anxiety-free and the J for joyazepam, then the null hypothesis that we want to test is that all 3 population means are identical, okay? So H subscript O, or H subscript 0, could be written out as mu of P for placebo equals the mu of A for anxiety-free equals the mu of J for joyazepam. So as a consequence, our alternative hypothesis is that the 3 population means are not all equal, okay? It is a bit tricky to write this mathematically, and there are a few different ways, right, in which it could make the null hypothesis false. But for now, we're just going to write a very simple alternative hypothesis. So H1 would be that not all of the mu subscript K are equal, okay? K equals the number of variables. So this null hypothesis, it is a lot trickier to test than any of the ones that we've previously seen. So then how are we going to do it? A sensible guess would be to do an ANOVA, since that's the title of the chapter, right? But it's not particularly clear why an analysis of variances would help us to learn anything useful about the means. In fact, this is one of the biggest conceptual difficulties for beginners that are learning this in stats that they report. So when they first encounter an ANOVA. So to see how this works, the author is saying that they personally find it most helpful to start by talking about variances. In fact, that's what they're going to do, is they're going to start by playing some mathematical games with the formula that describes the variance. So we're going to start out by playing around with variances, and then it will turn out that this gives us a useful tool for investigating the means, okay? So we're moving into section 13.2.1. We're looking at the 4th bullet, so we're looking at heading 2 formulas for the variance of y. So first, let's start by introducing some notation. We're going to use the big G, G like girl, to refer to the total number of groups. So for our data set, there are 3 drugs, so G equals 3 groups. Next, we're going to use big N, N like Nancy, to refer to the total sample size. So we have N equals 18 people in our data set. Similarly, we're going to use N subscript K to denote the number of people in the kth group. So in this, fake clinical trial data set that we're using for examples, the sample size is N subscript K, which equals 6 for all 3 groups. So they each have 6 participants. Finally, we'll use Y, big Y, to denote the outcome variable. All right. So in our case, Y equals mood change. It refers to mood change. Specifically, we're going to use Y subscript I, K, to refer to the mood change experienced by the ith member of the kth group. Similarly, we'll use y with the line over it to be the average, okay? The average mood change taken across all 18 people in our experiment. So the average big Y subscript K will refer to the average mood change experienced by the 6 people in group K. So now that we've got our notation essentially sorted out, we can start by writing down some formulas. So we have a really complicated variance formula on page 3. So to start with, let's recall the formula for the variance that we used at the beginning of our course. So way back in those days, we were just doing some basic descriptive statistics, and the sample variance of y is defined as what's listed below, okay? So just make a note of that equation for now. We have our variance of y equals 1 over n, and then we have two summations, one for g and one for n sub k, and then we have a parentheses which has y I k minus the mean of y, and then take that value and square it. This formula, it looks pretty much identical to our formula for the variance that we originally learned back in chapter 4. Now the only difference is that in this chapter 13, we have two summations in our formula. So the author is summing over groups, okay? For example, the values for K, and over the people within the groups. So for example, the values for I. And this is purely just a cosmetic detail of our formula. So if the author had used instead the notation big Y subscript P to refer to the value of the outcome variable for person, which is what P would mean in the sample, then they would have only have had a single summation symbol in the formula. The only reason that we have a double summation here is that they have classified people into groups and then assigned numbers to people within the groups. A concrete example might be useful here. So let's consider this table in which we have a total of n equals 5. So we have n equals 5 people sorted into G, which equals 2 groups. So arbitrarily, they're going to say that the cool people are in group 1 and the uncool people are in group 2. It turns out that we have 3 cool people. So n subscript 1 equals 3, and 2 uncool people, n subscript 2 equals 2, and then that totals 3 plus 2 equals our total of 5 between the two groups, and we're moving to page 4. So here we have data listed in our chart. So we have Anne, Ben, Kat, Dan, and Egg. That's person 1 through 5. So Anne, Ben, and Kat are in the cool group. Dan and Egg are in the uncool group. So that is person P 1 through 5. Which group they're in is K, so they could be in group 1 or group 2. The index for the group is little I, and we have 3 groups there, right? So there's 1, 2, 3, 1 and 2, and then we have our variable of mood or grumpiness, which could be denoted as either Y subscript P or Y subscript IK. So then we have our numbers of 20, 55, 21, 91, and 22. So notice that this author has constructed 2 different labeling schemes. We have a person variable P, so it would be perfectly sensible to refer to big Y subscript P as the grumpiness of the Pth person in the sample. For instance, the table shows that Dan is the 4th, so we'd say P equals 4. So when talking about the grumpiness Y of this person, whoever it is, we could refer to this person's grumpiness by saying Y subscript P equals 91. for person P equals 4, that is. However, that's not the only way that you could refer to that participant. As an alternative, we could note that this person belongs in the K equals 2 or the uncool group, and in fact, the person listed in this group is in the I equals 1 group. All right, so it's equally valid to refer to this grumpiness group by saying Y subscript IK equals 91, where K equals 2 and I equals 1. In other words, each person P corresponds to a unique IK combination, and so the formula that I gave above is actually identical to the original formula for variance, which would be variance Y equals 1 over 9, sum of N, and then Y subscript P minus the average Y, and then take that value and square it. So in both formulas, all we're doing is summing over all of the observations in our data set sample. Most of the time, we would just use the simpler Y subscript P notation. The equation is using Y subscript P, and it's clearly the simpler of the two. However, when doing the ANOVA, it is important to keep track of which participants belong in which groups, and we need to use the YIK notation in order to do that. So we're moving to section 13.2.2. We're at the bottom, and we're in bullet point 5. We're going to be going over from variances to the sums of squares now. So now that we've got a good grasp on how to calculate the variance, we're going to define something called the total sum of squares, which is going to be denoted as big S subscript tot, TOT, for the total sum of squares. It is pretty simple. Instead of averaging the square deviations, which is what we do when calculating variance, we just add them up. So we have SS total equals the sum of G, sum of N subscript K, and then we have our parentheses Y subscript I minus the mean of Y. Take that value and square it. So when we talk about analyzing variances in the context of analysis of variance ANOVA, what we're essentially doing is we're working with the total sums of squares rather than the actual variance. So one very nice thing about the total sum of squares is that we can break it up into two different kinds of variations. We have a within group variation and a between group variation. So an ANOVA is essentially taking the total variation measured by the total sum of squares and determining how much of that variation is due to differences within groups, and then how much is due to differences between the groups. So we can look at figure 13.2, and everything is depicted there. First, we're going to talk about the within group sum of squares. So let's go to the next slide. So we have within group sum of squares, and we're going to look at how different each individual participant is from their own group average, right? So we have our formula on page 4. So we have SSW, which denotes within group sum of squares, and then we have our same equation. So the summation of G, the summation of N subscript K, and then we have YIK minus the average Y subscript K, and then we take that value and we square it. So for this instance, we have the mean of Y subscript K. This is a group mean, right? So it's a group average. So in our example, this would be the average mood change which is experienced by participants that are given the Kth drug. So instead of comparing individuals to the average of all people in our experiment, we're only comparing them to those people that are actually assigned to the same treatment group. So as a consequence, you'd expect the value of SSW for the sum of squares within group to be smaller than the total sum of squares because it's completely ignoring any group differences. So for example, whether the drugs will have different effects on people's moods. And then next we can define a third notation of variation, which will capture only the differences between the groups. We can do this by looking at the differences between the group means, so the average y, subscript k, and the grand mean of y. Moving to page 5, we can take a look at figure 13.2. This is just a graphical illustration of the between groups variation in panel A, and then the within groups variation in panel B. So on the left, the arrows show the differences in the group means, and then on the right, the arrows highlight the variability within each group. All right, so in order to quantify the extent of this variation, what we do is we calculate between group sum of squares. So we have SS subscript B, and then we have the summation of G, the summation of N subscript K. Then we have the mean subscript K, so mean of Y subscript K minus the mean of Y. That value is squared. And then below that we have the reduction of those values. So it's not too difficult to show this illustration that the total variation among participants in the experiment, so SS total, is actually the sum of the differences between groups and the sum of the differences, the sum of the square differences within the groups. All right, so SS total equals SSW plus SSB. All right, so now that we found this out, we discover that the total variability associated with the outcome variable, or the SS total, can be mathematically carved up into the sum of the variation due to the differences in the sample means for the different groups. So SSB plus SSW, and then square that. So how does this help us find out whether the groups actually have different population means? So now that we think about it, this is exactly what we're actually looking for. So if our null hypothesis is true, you would expect that all the sample means are pretty similar to each other. And that would imply that you'd expect SSB to be really small, or at least you'd expect it to be a lot smaller than SSW. All right, so we're moving into section 13.2.3. We're going to look at a concept that goes from sum of squares to the F test, so F like Frank. So as we saw in that last section, the qualitative idea behind ANOVA is to compare the two sums of squares values, right? So SSB and SSW to each other, all right? So if the between group variation, SSB, is relatively large to the within group variation, then we have reason to suspect that the population means for the different groups are not identical to each other. So in order to convert this into a workable hypothesis test, there's a little bit of fiddling around that we have to do with our equations. So what this author is going to do is first show what we do to calculate our test statistic, which is the F ratio. And then they're going to try to give a feel for why we have to do it that way. So in order to convert our SS values into an F ratio, the first thing we need to calculate is the degrees of freedom associated with the SSB and the SSW values. So as usual, the degrees of freedom corresponds to the number of unique data points that contribute to a particular calculation minus the number of constraints that they need to satisfy. So for the within groups variability that we're calculating, it's the variation of the individual observations, so N data points around the group means, G constraints. So for the between groups variability, we're interested in the variation of the group means, the G data points, around the grand mean, the one constraint. Therefore, the degrees of freedom are as follows. So the degrees of freedom for between groups equals G minus 1, and the degrees of freedom for within groups equals N minus G. So that seems pretty simple. What we do next is we're going to convert our summed squares value into a mean squares value, and we're going to do it by dividing by the degrees of freedom. So let's see, for the mean squares of between groups, it will equal the sum of squares between groups divided by the degrees of freedom between groups. So for the within groups, we're going to do the mean squares W equals SSW divided by DF, degrees of freedom W. Finally, we're going to calculate the F ratio by dividing these two values. So the MSB divided by the MSW. All right, so we're dividing the between groups mean squares value by the mean squares value within groups. And at a very general level, the intuition behind this F statistic, it's pretty straightforward. So the bigger values of F means that the between group variation is large relative to within groups variations. As a consequence, the larger the value of F, the more evidence we have against the null hypothesis. So how large does F have to be in order to actually reject the null hypothesis? In order to understand it, you need a slightly deeper understanding of what ANOVA is and what the mean squares values actually are. So the next section discusses that in a bit of detail, but for readers who are not interested in these details of what the test is actually measuring, we'll just cut to the chase right here. So in order to complete our hypothesis test, we need to know the sampling distribution for F if the null hypothesis is true. Not surprisingly, the sampling distribution for the F statistic under the null hypothesis is an F distribution. So if you recall our discussion of the F distribution earlier in the course, the F distribution has two different degrees of freedom. The first one is degrees of freedom 1, and this is the between groups degrees of freedom. And then we have DFB, the second one, which is degrees of freedom 2. So let's say that again. So we have DF1, okay, which is the between groups degrees of freedom. So we're actually going to use DFB for that one. Then the second one is degrees of freedom subscript 2, which is your within groups degrees of freedom. So that one is denoted as degrees of freedom subscript W. You also, you may also call these just numerator and denominator degrees of freedom respectively. So a summary of all of the key quantities that are going to be involved in a one-way ANOVA analysis include the formulas showing how they are calculated. So we're going to look at table 13.1 this is going to exclude our p-value, which has a very high and a very complicated formula, and it would be pretty nightmarish to try to calculate it by hand. So we're going to let the software do it. So here, let's look through this, this summary table. So table 13.1, it basically includes our key quantities involved in an ANOVA organized into a standard ANOVA table. So we have row of between groups and we have row of within groups. We have our formulas for degrees of freedom. We have our sum of squares formulas. We have our mean squares formulas. We have our F statistic formula, and then we have our complicated p-value. So in addition to the values seen in this table, 13.1, which is on page 6, occasionally you will also see a total row at the bottom. The total row will only include values for the degrees in freedom and sum of squares. In both cases, the total is equal to the sum of the between groups and within groups values. So it can be written just like it is at the bottom of page 6. So it can be written as degrees of freedom total equals degrees of freedom subscript B plus degrees of freedom subscript W, which can then be rewritten as the sum of squares total equals the sum of squares B plus sum of squares W. So we're going to move into page 7, and we're going to go through section 13.2.4, and we're going to look at the model for the data and the meaning of F. So at a fundamental level, the analysis of variance, the ANOVA, it's essentially a competition between two different statistical methods. And so when we described the null and the alternative hypotheses at the start of this section, the author was a little bit imprecise about what these models actually are. So now we're going to go through that. So if you can recall, the null hypothesis was that all of the group means are identical. So a natural way to think about the outcome variable, so the big Y subscript IK, is to describe individual scores in terms of a single population mean, or mu, plus the deviation from that population mean. So this deviation is usually denoted as epsilon IK, and it is traditionally called the error or the residual that's associated with that observation. But here we want to be a little bit careful. So just like we saw with the word significant, the word error, it does have a technical meaning in statistics that isn't quite the same as it is in everyday English. So in everyday language, error implies some type of a mistake, but in statistics, it doesn't, at least not necessarily. So with that in mind, the word residual, it is a better term than the word error. So in statistics, both words mean leftover variability, which is essentially the stuff that the model cannot explain. So in any case, here's what the null hypothesis looks like when we write it as a statistical model. So it would look like this equation. So Y subscript IK equals mu plus epsilon IK. So this is where we make the assumption, which will be discussed later, but we're making an assumption that the residual values, or the epsilon IK, are normally distributed, with the mean 0 and a standard deviation, or a sigma, that is the same for all the groups. In statistical notation, we would write this assumption as follows. So epsilon IK is approximately normal, and then we have a coordinate of 0, sigma squared. So what the alternative hypothesis, what is that? Okay, so how are we going to write the H1? So the only difference between the null hypothesis and the alternative hypothesis is that we're going to allow each group to have a different population mean. So if we let the mu subscript k denote the population mean for the kth group in our experiment, then the statistical model corresponding to H subscript 1 is this equation. So it would be y subscript ik equals mu subscript k plus epsilon ik, where once again we're going to assume that the error terms are normally distributed with mean of 0 and a standard deviation of sigma. So that is the alternative hypothesis also assumes epsilon is approximately normal with a coordinate of 0, sigma squared. So now that we've described our statistical models and the underpins of the null hypothesis and the alternative hypothesis in more detail, it's pretty straightforward to say that the mean square values are measuring. It's pretty, straightforward to say what they're measuring, okay, with the mean square values and what this means for the interpretation of the F statistic. So we're not going to bore you with proof of this, but it does turn out that the within groups mean square, the MSW, can be viewed as an estimator of the error variance sigma squared. The between groups mean square, or the MSB, it's also an estimator, but what it estimates is the error variance plus a quantity that depends on the true differences among the group means. So if we call this quantity big Q, then we can see that the F statistic is basically this equation. So F equals Q, the estimated Q, plus the estimated sigma squared divided by the estimated sigma squared, where the sigma, right, denotes standard deviation. So where the true value of big Q equals 0, hold on, let me back up here. So we can see that our F statistic is basically where the Q value equals 0 if the null hypothesis is true, and the Q is greater than 0 if the alternative hypothesis is true. So at a bare minimum, the F value must be larger than 1 to have any chance of rejecting our null hypothesis. So make a note that this does not mean that it's impossible to get an F value of less than 1. What it means is that if the null hypothesis is true, the sampling distribution of the F ratio has a mean of 1 cubed. And so we need to see F values larger than 1 in order to safely and accurately reject the null hypothesis. So to be a bit more precise about the sampling distribution, notice that if the null hypothesis is true, then both the MSB and the MSW are estimators of the variance of the residuals of epsilon ik. So if those residuals are normally distributed, you might expect that the estimate of the variance epsilon ik is chi-square distributed, because that's what a chi-square distribution is. It's what you get when you square a bunch of normally distributed values and then you add them up. So since the F distribution is, again, by definition, what you get when you take the ratio between two things that are chi-square distributed, and we have our sampling distribution. So we're just going to gloss over this stuff in very broad terms. And this is basically what you need to know, is that this really is where the sampling distribution actually comes from. We're going to move to page 8 and we're going to work on our example. So the previous discussion, it was fairly abstract and a little bit technical, but the author is stating that at this point it's going to be more practical and more helpful to do the example in JASP. So for that, we're going to go back to our fictitious clinical trial data set that we introduced earlier. The descriptive statistics we calculated at the beginning tell us our group means, which is an average mood gain of 0.45 for the placebo and average mood gain of 0.72 for anxiety-free and average mood gain of 1.48 for joyzepam. Keeping that in mind, let's go ahead and do first some long calculations before we work it in the software. So we're just going to do this for the first 5 observations. So let's start by calculating the sum of squares for within groups. Okay, so we're going to draw up a table to help us with our first 5 calculations. So here's a table on page 8 where we have our group of K, which is placebo, 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 anxiety-free, anxiety-free. Our outcomes are on the right, so we have our outcome, Y subscript IK, and our values of 0.5, 0.3, 0.1, 0.6, 0.4. So at this stage, the only thing that the author has included in this table is just the raw data. So that is, it's the grouping variable for drug and the outcome variable for mood gain for each participant in that group. So note that the outcome variable here corresponds to the YIK value for our previous equation. The next step in the calculation is to write down for each person in the study the corresponding group mean, so the average Y subscript K. This is slightly repetitive, but it's not particularly challenging since we have already calculated those group means when we did our descriptive statistics. So we have a third column that we're adding here. This column is the group mean, so it's the mean Y subscript K. So we get 0.45, 0.45, 0.45 for the placebo, and then for the anxiety-free, 0.72, 0.72. So now we've essentially written these down, and then we just need to calculate for each participant the deviation from the corresponding group mean. So we want to subtract YIK minus the mean of Y subscript K. So after we've done that, we're going to square our values. So here's our column 4 and column 5. So in column 4, we have the deviation from the group mean. So we have YIK minus the mean of Y subscript K. So we get 0.05, negative 0.15, negative 0.35, negative 0.12, negative 0.32, and then we square those. So we get 0.0025, 0.0025, 0.1225, 0.0136, and 0.1003. That last step, it's pretty straightforward, and then in order to calculate the within group sum of squares, we just add up the squared deviations across all observations. So we're going to add that column 5. So we add all of those, and we get the sum of squares for the within groups equals 0.2614. We're going to move to page 9. So if we actually wanted to get the right answer, we just need to do this for all of our 18 observations in this data set, and not just for the first 5. We could continue with doing the hand calculations if we wanted. Since it's pretty tedious, we're just going to do it in our software. And then we're going to end up with a within group sum of squares value of 1.39. So that's the SSW, and we'll keep going. So now that we've calculated the within group variation, the SSW, we're going to now calculate the sum of squares for between groups. The calculations will be very similar. The main difference is that instead of calculating the differences between an observation of yik and a group mean of the mean yk, for all of the observations, we're going to calculate the differences between the groups of mean yk and the grand mean y, and which in this case is 0.88 for all of the groups. So we have a new chart here. So we have our placebo, our anxiety-free, and our joyzepam arms. And then we have our group mean, we have our grand mean, we have our deviation, we have our squared deviations. So for the between group calculations, we need to multiply each of these squared deviations by n subscript k, the number of observations in the group. We do this because any observation in the group is associated with a between group difference. So if there are 6 people in the placebo group and the placebo group mean differs from the grand mean by 0.19, then the total between group variation associated with these 6 participants will be 6 times 0.19, which will give you 1.14. So now we're going to extend our table of calculations. So we're going to add 3 more columns. So now our between group sum of squares is obtained by summing these weighted squared deviations, and we're going to add up that last column, so 1.14, 0.18 plus, so those two plus 2.16, and we get SSB equals 3.48. As you can see, the between group calculations are a lot shorter. So now that we've calculated our sum of squares for SSB and SSW, the rest of the ANOVA should be relatively painless. The next step is to calculate degrees of freedom. So since we have G equals 3 groups and N equals 18, we have our calculation as follows. So for the degrees of freedom between groups, that will equal G minus 1, which equals 2. For our degrees of freedom within groups, it will be N minus G, which will be 18 minus 3, which will give 15. Next, since we've calculated values for sums of squares and degrees of freedom for both within group variability and between group variability, we can obtain the mean square values by dividing one by the other. So we can do MSB, which will equal SSB divided by degrees of freedom B. That equals 3.48 divided by 2, which gives us 1.74. The MSW equals SSW over degrees of freedom W. That is 1.39 divided by 15, which gives us 0.09. The mean square values can be used to calculate the F value. Again, this is the test statistic that we're actually interested in. We do this by dividing the between groups mean of squares value by the within groups mean of squares value. So that's F equals MSB divided by MSW, which equals 1.74 divided by 0.09. So we get an F statistic of 19.3. We're going to move to page 10. So now that we have our test statistic value, the last step is to find out whether the test itself gives us a significant result. So back in the day, what we'd do is we'd open up a statistics book and we'd go to the huge table and we'd look up the threshold F value corresponding to a particular value of alpha. So for example, 0.05 or 0.01 or 0.001 for the 2 and 15 degrees of freedom. So doing it this way would give us a threshold F value for an alpha of 0.01 of 11.34. So as this is less than our calculated F value, we can say that P is less than 0.001. But that was the old days, and nowadays we're just going to use our software here, and it's going to calculate the p-value. So in fact, the exact p-value is 0.000071. So unless we're being extremely conservative about type 1 errors, we're pretty much guaranteed that we're going to reject our null hypothesis. So having completed these calculations, it's then traditional to organize all these numbers into the analysis of variance table. So for our fictitious clinical trial data set, the ANOVA table would look like this. So we would have we're on page 10, we would have between groups with 2 degrees of freedom, sum of squares 3.48, mean of squares 1.74, F statistic of 19.3, p-value is very small, 0.000071. Then the within groups row is degrees of freedom 15, sum of squares 1.39, mean of squares 0.09, and there is no F statistic and no p-value. So in these days, we're probably never going to have much reason to need to construct that table, but you will find that almost all of the statistical software, including JASP, it does tend to organize the output of an ANOVA into this type of a table. So it is a good idea to get used to reading these tables for ANOVA, analysis of variance, statistical test. And although the software will do the output of a full ANOVA table, there's almost never a good reason to include the whole table in your analysis or your write-up summary. A pretty standard way of reporting this result will be to write something like this. A one-way ANOVA showed a significant effect of drug on mood gain. F2,5 equals 19.3, P less than 0.001. And next we're going to actually run a one-way ANOVA example. So a one group, we're going to run the one-way between groups ANOVA and JASP. And so here we go. So we're going to go back into JASP and pull this up. We're going to go to ANOVA, all right, which is right up here in the top setting. Okay, ANOVA. And we're going to go under classical and select ANOVA. There we go. And then we're going to move mood gain to the dependent variables box. And then we're going to move drug to the fixed factors box. We're going to check the box next to estimates of effect size. Okay. And we're going to check the box for n squared and uncheck w squared. This should give the same results that we'll see in figure 13.3. So let's check. All right, so we have our ANOVA for mood gain. We have our, we can blow this up. So we have our sum of squares for drug of 3.453. We have our residuals of 1.392, 2 and 15 degrees of freedom, mean square 1.727, 0.093, F is 18.61, and the P is less than 0.001, and the n squared is 0.713. Looks good. All right, so let's go back here. So we do want to make a note that the software for JASP, let's see. The JASP software is known to be more accurate than the ones that we free-handed above. Due to, a lot of statisticians, it's possible to make human errors like rounding errors. So this software is more accurate typically than the hand calculations. Also note that we checked the n squared box, which is actually pronounced eta squared. And we will come back to effect sizes in a little bit. The JASP results in figure 13.3 are showing again the sum of square values, the degrees of freedom, and a couple of other quantities that we're not interested in yet. And notice, however, that the JASP software does not use the names between group and within group. Instead, it assigns more meaningful names. So in this particular fictitious dataset example, between groups variances actually corresponds to the effect that the drug has on the outcome variable, and the within groups variance corresponds to the leftover variability or the residuals. So if we compare these numbers to the numbers that we calculated by hand in the previous section, you can see that they're pretty much the same apart from some rounding differences. The between group sums of squares is SSB equals 3.453, and the within group sums of squares SSW equals 1.392, and the degrees of freedom are 2 and 15 respectively. We also get our F value and our P value, and again, these are more or less the same as we previously calculated by hand. So let's keep going. The next section is going to look at effect size. So we're in section 13.4. So let's go back here for a second. All right, so there's a few different ways that you can measure the effect size in ANOVA. The most commonly used measures are the eta squared, which looks like the n, fancy n squared, or a partial a test squared, which looks again like a fancy n squared. Now, in this one-way between groups analysis of variance, they're pretty much identical to each other. So for now, we're just going to go over explaining the a test squared. The definition of the a test squared is actually really simple. A test squared equals the sum of squares between values divided by the sum of squares total. And that's all it is. So when we look at the ANOVA table in figure 13.3, we can see the SSB equals 3.45, and the SS total, let's go back here, and the SS total equals 1.39. Therefore, we get a value of 3.45 divided by the value of 4.84, which is our SS total, right? So that would be, if we added those together, that would be our 4.84. So 3.45 divided by 4.84 equals 0.71. All right, so we see that at the end, right? That last column. Now, the interpretation of the a test squared, it's equally straightforward. It just refers to the proportion of the variability in the outcome variable, okay, which is mood gain, which can be explained in terms of the predictor drug, okay. So again, let's say that. So the interpretation of the a test squared of 0.71 or 0.713, it's straightforward. It just refers to the proportion of the variability in the outcome variable or mood gain. That can be explained in terms of the predictor, which is the drug given. So a value of a test squared of 0 means that there is no relationship at all between these two variables. Whereas an eta squared of 1 will mean that the relationship is a perfect relationship. Better yet, the eta squared value is relatively closely related to the r squared, and it has an equivalent interpretation. So now we're going to look at bottom of page 11. We're going to look at section 13.5, and we're going to look at multiple comparisons and the post hoc tests. So anytime you run an ANOVA with more than 2 groups and you end up with a significant effect, the first thing you probably want to ask is which groups are actually different from each other. So in our drugs clinical trial example, okay, so our data set example, our null hypothesis was that all 3 arms of the study, the placebo, the anxiety-free, and the joyazepam, that they all have the exact same effect on mood. But if you really think logically about it, the null hypothesis is claiming that 3 different things, right, would all be the same, which logically can't be the case. So let's back up here. So the author's saying, if you think about it, the null hypothesis is actually claiming 3 different things all at once here. And specifically, it claims that your competitor's drug, anxiety-free, is no better than a placebo, okay? So the mu of A equals the mu of P. And that your drug, the joyazepam, is no better than a placebo. So the mu of J equals the mu of P. And that your anxiety-free and joyazepam treatment arms are equally effective, that the mu of J equals the mu of A. So if any one of those three claims turns out to be false, then the null hypothesis is also false. So now that we've rejected the null hypothesis, we have to think about like which one of those things is not true, okay? So we're thinking that at least one of those things is not true. But which ones? So all three of these propositions are of interest. Since you certainly want to know if your new drug, joyzepam, is better than a placebo, it would be nice to know how well it stacks up against an existing commercial alternative like anxiety-free. So it would even be useful to check the performance of anxiety-free against placebo. So even if anxiety-free has already been extensively tested against placebo by other researchers, it can still be very useful to check that your study is reliable, right? So that it is producing similar results to the earlier research. So when we characterize the null hypothesis in terms of these three distinct propositions, it becomes clear that there are actually 8 possible things that we need to distinguish here. So if we list it out in terms of possibility 1 through 8, and then is the mu of P equal to the mu of A? Is the mu of P equal to the mu of J? Is the mu of A equal to the mu of J, right? And then which hypothesis, right? So null or alternative. So by rejecting the null hypothesis, we then have decided that we don't believe that that the scenario listed in possibility number 1 is true. The next question that we ask is which of the other 7 possibilities might be right. So when faced with this situation, it's usually helpful to look at your data. For instance, if we look at the plots back in 13.1, figure 13.1, it's tempting to conclude that joyzepam is better than the placebo and better than anxiety-free, but there's no real difference between anxiety-free and the placebo. However, if we want to get a clearer answer about this, it might help to run the post hoc test. So we're going to pause here and then we're going to come back and look at running the pairwise post hoc t-test.